better this way? You can hear it better that way? Okay, I'll try to keep, you gotta keep the mic right tight, and that's what gets frustrating. You may wonder how come I'm talking about the Brooklyn Bridge as a barn builder. As a barn builder, I work with timbers, and believe it or not, there are timbers in the Brooklyn Bridge, and timbers that had to be repaired in the Brooklyn Bridge, and that's what caught my eye. Now the other half of this story has to do with why I even got connected with the Brooklyn Bridge at all, and that has to do with somebody in the room today. I drive ambulance up in Casanova every Sunday night, and I relieve Tom Siegel. He drives Sunday afternoon, and he was telling me about the digging of the foundation of the Brooklyn Bridge and how they would take the dirt and throw it under these pipes, and the pressure down in the bottom of the foundation push the dirt right up through to the top and blow out. I said, oh, that's crazy. How can that happen? So the next week he brought me the book. This book by David McCullough on the building of the Brooklyn Bridge, and showed me the passages dealing with that. So that's when I started reading about the bridge and found out about the timbers in the bridge. And so today I'm going to tell you about the timbers in the bridge and the repair of those timbers. Before we go there, I'm going to get a little bit of history. This picture is from January of last year. I drove my daughter down to New Jersey to pick up her car that had just been floated across from Europe. She was in the Air Force, and they brought her car back. We brought her car back. And on my way home, I took the back way. I went over to the bridge to take a few pictures of the bridge. And these are my first encounter with the bridge in person a year ago on a beautiful January day. These first shots, I was just sitting in the car, zeroing it in on the top of the tower. When you get sick of looking at it, it's like, no. Here I am walking up the promenade, I'm on the Brooklyn side, looking at Manhattan. And you can see the traffic on each side, and then we work way up through. Now, one thing with the bridge, unfortunately, when I was there, is that they were working on the bridge, and areas of it were shielded off. It's an impressive structure and a very quite romantic structure aesthetically to look at and walk on. Certainly, you could consider it the most, one, if not the most famous bridge in the world, maybe, or at least on North America, next to the Golden Gate. Now I'm at the Brooklyn Tower, the base of the Brooklyn Tower, and if I look off to my, facing west, if I look off to my left, I'm looking at the Statue of Liberty. I'm looking southwest, next shot. And if I look off to my right, off to the northeast, I'm looking at the Manhattan Bridge, which was built in the 20th century. And if you look down through here, you start seeing that this bridge dates back, was started just after the Civil War. And as you walk up to it, it doesn't look that old, but you start looking at the ironwork in the bridge. Next shot. You can see that that's the ironwork that's been there for since the 1870s. Now here's the designer of the bridge. And I'm going to give a little background on the Roebling family. John Roebling is an immigrant from Germany. He went to school in Germany for engineering. He came over here and started believe it or not, a utopian farm community outside of Pittsburgh. but he really wasn't into farming. He always had he wasn't patient enough for it, and he enjoyed, he got involved in wire ropes. He had a fascination with wire ropes, and he bought some machinery that actually wound up wire ropes, and he made a fortune, his fortune, dealing with making wire rope. Now his first bridge that he designed was over the Niagara River in Niagara Falls. That's Niagara Falls way in the background there. Next slide. He built it in 1848, that's the actual bridge right there. He got, too fast, going back one. He was fascinated with the concept of the tension compression of a suspension bridge. And these suspension bridges are relatively new at this time, mid-19th century. His next bridge was in Pittsburgh over the Allegheny River. And it was this bridge that his oldest son, who was a graduate of Rensselaer Poly over in Troy, helped him. Next picture. And started getting involved in the bridge business. The third bridge he built was going to be the largest bridge in the world at that time. It was in Cincinnati over the Ohio River. Another suspension bridge. And that's it there. And his son, after the Civil War, he actually did all of the work involved in finishing this bridge. Next slide is Washington. Roebling was built bridges for the Union troops during the war, fought in 8 battles, was decorated, and actually ended up being a colonel. And actually is an interesting character in the sense that he wasn't the sort of loud, aggressive person his dad was, but he was very confident and quiet. Next slide. Now this slide, in 1867, John Roebling, in 3 months, put together all the documents, preliminary documents, for the Brooklyn Bridge. And in 1869, the municipalities agreed to try to put the bridge together. And so in 1869, John and Washington were out on the end of a pier. And John was on the very tip of a pier that had a whole bunch of telephone poles all hooked together. And a ferry was coming in, and he decided he better step back and get away from the ferry, but his foot was still in between some of the poles, and when that ferry came in and hit the pole, his foot got smashed in between it. The bridge, forgot to mention, the bridge is going right across this area, right about in here in southern Manhattan. He ended up getting tetanus from it, and 17 days later he died. Next slide. So at 32, his son ended up having to, he's the one that built the bridge that his dad designed. So at 32, he was going to be building the largest bridge in the world. Just to give you some idea of some of the important concepts, basic concepts of the bridge as we look at some of the pictures. I'll also give you some of the spans. We have our 2 towers, and there's a Brooklyn side and a New York side. And we have the bridge work itself, the roadway, and the span. The span between the towers is 1,595 feet and 6 inches. The land span between the towers and the anchorages is 930 feet on each side. And the approach on the Brooklyn side, coming up to the anchorage, is 971 feet. And on the New York side, the approach was 1,562 feet and 6 inches. So the total length of the bridge was 5,980 89 feet, over a mile long. The height of the towers from the sea level to the top was 279 feet. (276 feet, 6 inches). And the height of the bridge at the maximum point was 135 feet, I believe, from sea level to the underside of the bridge. Now we have the towers that are under compression, the bridge works, the cables that are under tension, and the anchorages, which are quite important because this tension has to be picked up at the anchorages at the bridge, at the end of the bridge. Next. I'm going to focus a little bit of attention on the cables because they're really the most interesting. My next slide is going to show what's going on up in the top of where those cables come into the top of the tower. Here you can see the cables coming in, and they're riding on cast iron shoes. Next slide. You can see this is what they're riding on, and they're actually on rollers here so they can actually move around. It's not rigid. And if you look at these cables, you can see there's a whole bunch of little bitty wires in parallel there. Next slide. Go up backwards. There we go. This shows the actual weaving, shouldn't call it weaving, running of these cables back in the late 1770s. Next slide. You can see it's just these, this is individual wires a little less than a 1/4 inch thick that were run. Next slide. To give you some idea of how many, I've had conflicting information on it. I believe there's 300 of those 1/4 inch wires in each strand, and there's 19 strands. So it's almost 6,000 of these wires for each cable. Each cable was capable of holding 24 million pounds. The cable itself weighs 1,700,000 pounds. Now the wires, all the wires are made on the Brooklyn side, and all the drums holding the wires are on the Brooklyn side of the bridge. And the wires, when they came to the bridge, were only about 300 feet in a roll. And so they had to splice these wires together, and this is how they did it. This is a little confusing because this looks huge, but that's actually less than a 1/4 inch. That's the end of the wire, and that ferrule threaded into it, and the threads are opposite of each other, so as you tighten it, the two pieces come together. And then they rounded these edges, and they would form a continuous wire. And in every strand that had 300 wires in it, that was one continuous wire back and forth the whole time. There was no break in it, except for these ferrules that connected the wires together. Now the actual amount of wire in the bridge.
I got a question.
Yeah.
The ferrule is tapped, it has a tap. Now, how do you put a thread on the outside of the wires to engage the ferrule?
As I read the book, these questions popped into my head, and I would have loved to have seen the machinery and the pictures that did all that. The only thing I can tell you is that it did happen, and it happened in 1870, and they had the machinery to do it.
Because I read the book.
It wasn't in there.
Yeah.
It wasn't in there. You know, there's a lot of information from a builder's point of view that I would have liked to have had at the time. Dealing with the wires, there was over 3,515 miles of wire in each cable. Next slide. Now the actual stringing of this wire is kind of interesting. Here's the Brooklyn side. They would run they have a big spool in a warehouse in the back here. They'd run that wire, pull it. There was a rope, a wire rope that was on in a loop that ran from the Manhattan side to the Brooklyn side. And on that wire, there was a pulley that you could hook the wire to. And that loop was set on a drum that they could spin forward and backwards. And they would just take that pulley and run it, let's say turning the drum forward, that pulley would run all the way up and over the towers, and down and up and over Manhattan Tower, down to the anchorage. And at the anchorage, they would take that loop and they would hook it onto, go to the next slide. That shoe right there. Now, the wire was 2 wires. It wasn't 1 wire that was being pulled over. And I think that helps. If I can demonstrate, it looks like there's some baling twine here if you're interested, if that's confusing or not. Here we go. Just on the twine now. Imagine that what Bill is holding is a big spool on the Brooklyn side. And that the pulley that I'm holding is on what they call the traveler rope. And it goes on to that end. That end gets refastened to the anchor. And as I pull across the bridge, like this, you see I got 2 wires going at the same time. And when I got to the Manhattan side, I would disconnect the pulley, and I got this loop. And that loop is what goes on there. Now the other thing with the traveler rope is that now I got this pulley on this side, I got to get this back to the other side. So they're going to take that rope and spin it backwards. And so this goes back to the other side empty. But that rope, as it's going back to the other side of the rope is going over to the Manhattan side, the New York side. There's another pulley there. So as this one's going back, there's a pulley pulling another section of wire across. So it took about 10 minutes for this to happen, and you end up getting four strands across. And each one of those strands, each one of those strands is a continuous wire. There's no breaks in it. And it took about 2.5 years for them to complete all the cabling in the bridge. Build the 4 cables, hang all the cables that would hold the bridgeway. Which is better? With this? Oh no, me just talking? Okay.
Right.
Sounds good. I have to pay attention to holding the mic. This picture just shows the, and I should mention too, go backwards 2 slides. One more. Oh, too much, right there. Notice these little bridges here. As they're running that cable up and over the tower, there was men along there making sure that everything was nice and parallel. When they got to the tower, they stopped and they would pull or tighten it up, and so the wires were actually perfectly parallel to each other before they took off again, because they had to be right tight the whole time. Okay, so this just shows, you see here are the strands, and here they're wrapping those strands and another coating and another wire on it so that no water can get in there, so they can't rust out the strands themselves. Next slide. Now, if you look at this is the pictures back a year ago. If you look at these cables, these are all brand new. Back in the mid-50s, they redid the bridge. They changed the roadway, and the suspension cables were replaced. Next slide. But the main cable in the bridge, that's the original one. To replace that would have been a monumental job. This is all new stuff hung on that main cable right there. And that cable right there is the one that has 6,000 little wires in it. It can carry about 24,000 pounds. Now the actual weight of the superstructure, the bridge, the suspended part of the bridge is about 13,000 pounds. So then if you add in the weight of the cables, you have about 20,000, a little over 20 million pounds, I mean, of weight. 20 million pounds of weight. And one cable could carry all the weight of the bridge. So you got 3 other cables in there. And in any engineering, they always factor in at least a factor of 3 to 4 of safety involved, and they feel that it's safe.
Randy, what's the diameter of the main cable?
This main cable here is 16 inches, 15 3/4. But
And the covering is a wire wrap?
that is, if you look close, you see that there's little wires going around it.
No, they've never had to replace that wire wrap?
I don't know. I can't tell you. You do wonder about that, because you just sort of saw through there and that's it. You know, that rusts through, and the way everything goes, that's for sure. Next slide. Now the anchorage, an important part of how you take this tension and you know, and counteract it. I counteract it by bringing all these cables in, and these are big links of chain. It's essentially just like a chain, bicycle chain even, except these are 10 feet long and 2 inches thick. It's huge chain. It goes through this anchorage, and it's hooked in the bottom, and all the weight of all the stone is on top of this iron anchor. Next slide. It shows a picture of the actual anchorage. I don't know which side it is, if it's Brooklyn or New York next. And here's that chain. Here you can see a strand coming in, and it loops around right there, that comes back out. Over here, this cable has been done. It's a little complicated. That cable's been done, and they're working on the other cables down through. This one, they're just wrapping it up, and they're just starting the outside cable over there. Next slide. So these are the chains. Look, here shows the cables coming in. Next. And you can see they're coming in here, and this chain goes all the way down. And there's like 7 or 8 of them alongside each other right down through there. Carrying them. Next. The floor itself, the roadway. Now we do have the beams that go from cable to cable, and then the roadway sets on those beams, and then you have these trusses. Now, what's going on with these trusses? Here we got this cable hung over 1,500 feet between towers, and it'll have a tendency to go like the whole structure kind of move like this. And so, if it's just hanging there, this structure right here, this box, is what's got to keep it from moving back and forth in the wind, and that's why you have those trusses in there. Next slide. Here shows the building of the putting the steel beams across. Now they just worked from one tower, started both towers, and just worked in each direction towards the anchorage and towards the center of the river, hanging wires down and then hanging the steel in between them, and then you put your platform on top of the beams.
How many men are working on this project, during this project?
Well, it depends. The project started in 1869. It finished in 1883. And in the wintertime, it was shut down because of the bad weather. So, and there's a lot of things going on at the same time. I never saw a figure that said there was this many people working on it. It would depend on what phase, what time of year, and what section of it. You had masons working, you had people dealing with winding cable, people building road. I know in the digging of the foundation, there was usually about 100 to 200 men down in the hole digging at one time. That's what we'll talk about a little bit later. Notice this little catwalk. When they first went across, one of the first things they did was put that catwalk across. And there was a point when they had the two towers up, you had to run the first wire rope over. And they carried a rope up and over the Brooklyn Tower and let it come back down to the river, and then a boat. They had to wait for all the traffic to kind of clear, and a boat went across the river with that cable. They just let it drop into the bottom, the cable. Then they carried it up and over and down, and then they pulled that tight when there was no traffic coming. That was their first wire. And there was actually a man that went across that wire for the first time. They made a big deal of it. He was one of the foremen. He was literally on just a pulley, a rope, and a board this wide, sitting there, and he went across for the first time, and they pulled him over. But people could walk across this catwalk. It was wide open. You could walk up to the bridge, and this catwalk would go up and down and right down to the anchorage, and people would walk up to them and walk up and down. Just another picture of them. It kind of looks sort of eerie. You see this platform kind of going out over it, but it's being, remember, it's being suspended off, the weight is being suspended off of these cables. Right? Next slide. Next. This shows the change in the deck. 1883, trolley, horses. In the mid-50s, they got rid of the trolleys, and it's 3 lanes of highway going across. And here's the promenade through here. This was 85 feet across. Next slide. This is back in January. You see the 3 lanes of traffic. This lane here used to be a trolley. Next. Now I've gone a little bit on the construction of it, but I haven't said anything about timbers. I haven't said anything about the foundation. What's this tower? What's all this stonework setting on? And actually, what's interesting is that basically all the stonework is something they knew how to work with. It's just big chunks of stone laid on each other. The cables was something that John Roebling had invented. He had done it 3 times before, and they knew what was going on. But dealing with the foundation that went under this bridge, that was the big problem. This was the unknown. Next slide. How do we dig a hole to get that stonework down on bedrock through the East River? And it's on the Manhattan side, bedrock was 90 feet below the sea level. So how do we dig a hole down there and start building that stonework up? This is what we're going to investigate here a little bit. This is where the wood comes in. Next slide. They built what they call a caisson out of wood. And I'm going to throw a little multimedia here. I know it'll come up. I had it set on, but I'm going to go back and
Caisson, 1869 to 1872. April 9th, 1870. For those not acquainted with the process, we may say that a caisson is an inverted wooden box on which the towers are constructed.
underneath.
As it rests on the riverbed, a hollow space called air chamber is formed beneath it. Compressed air is forced into the chamber until the water is entirely displaced. The chamber is entered by laborers who undermine the edges of the caisson while masonry is built on top of it, causing in this way a steady, gradual descent through the riverbed until it's grounded on bedrock.
In theory, it worked. Small caissons holding 1 or 2 men had been used in Europe. But the nature of the difficulties in sinking a caisson half the size of a city block could hardly be foreseen. Uncertain that caissons of such extraordinary size could even be built, the shipbuilders who were to construct them refused to guarantee their safe delivery and demanded all the money in advance. The first caisson would be built for the Brooklyn side of the river.
70,000 tons of stone and brickwork are to be piled upon the caisson, which now floats lightly on the surface of the East River. All the weight of every man, woman, and child in this city would be but a fraction of the weight of building materials this wooden caisson will have to bear.
Few people in New York at that time realized how complex the caissons actually were, that Washington Roebling designed every feature. He devised an airlock for admitting the workmen, and an ingenious method of removing the earth and rock without allowing the compressed air inside to escape. A shaft was passed through the roof of the caisson. It was filled with a column of water, the water held precariously in place by the force of the air inside. Through it, a giant clamshell dredge could move freely as it carried the debris up and out of the caisson to waiting barges. Each decision was described in a drawing, hand-painted with meticulous care, often by Roebling himself, for the benefit of those craftsmen who couldn't read or speak English. On paper, it all worked perfectly.
June 1870. The bed is so rocky that in place of 1 month, 5 are required to do the work. These are 5 months of incessant worry and toil, everlasting breaking down and repairing, and constant study where to improve if possible.
For Roebling and the men working inside the caisson, with all that weight bearing down overhead and the river outside, it was a terrifying and eerie experience. The force of the compressed air made pulses race, made voices thin and unnatural. It made the danger of fire very serious. Flaming calcium lamps lit one chamber, while the rest of the caisson lay dark and slimy with river mud. Often explosions of compressed air escaping under the edges plunged the men into total darkness as several feet of water rushed in. It was said that Washington Roebling was the only one who kept his head.
June 15, 1870. Rate of descent not half a foot this week.
The caisson of the East River Bridge was severely damaged by fire yesterday. I don't believe any man now living will cross that bridge.
I am the chief engineer, and I'm in constant attendance day and night except time for sleep. A fire broke out Thursday evening, and I stayed down until about 5 o'clock. I felt I should be paralyzed if I stayed down another minute. I was partially paralyzed, but not quite over it now.
The dam.
That's it for it. Okay, caissons. Actually, that little blurb doesn't do justice to what was going on with these structures and what happened down in the digging these out. To give you some idea of the size of this caisson right here. The caisson itself was 168 feet long and 100 feet wide. This room is 45 feet long and 33 feet wide. So it's at least 3 lengths of this room, 3 widths hooked together to give you the width of it. Let's see, a 45, we need four of these rooms in that direction. And so we're dealing with 12 of these rooms together to give you the size of this caisson. It was built out of 12 by 12, a yellow pine bolted together. The distance in here for the digging was 9.5 feet. And down at the bottom here, this cutting edge, that was a cast iron piece 8 inches wide that went up on 2 sides, and the whole outside of it was covered in metal. When they floated it, when they first, they built it in a shipyard, it was 14 feet high. There was 5 feet of solid wood right here, as you can see. So there's this huge like platform just floating down the East River, and they would float it exactly where they wanted to drop it, and they would anchor it there. And then they would start building, putting stones. Well, actually, they started putting more timber work on top. But this timber work they put on top from there on in was, in between the timber, they put in concrete. You can see that lattice work there. In between these timbers, that was concrete. They start filling this up until it got heavy enough that it would stay down and hit the bottom. Now, this is in the ocean, so every day it was going up and down with the tide. This whole thing was going up and down. And it would actually go down, and low tide would hit the bottom. And on the Brooklyn side, they actually would pump out the air and go down and start digging for a while, and then it would float back up again. And they couldn't dig anymore. So, now the total height of the Brooklyn side from the very bottom of the cutting edge to the top of the wood up here was 21 feet. The height of this room, 18 feet. So the thickness of that caisson was 2 feet higher than the height of this room. 12 of these rooms, 2 feet higher, gives you an idea of that caisson. Now on the New York side, because he had to go, on the Brooklyn side, they could hit bedrock at 45 feet. On the New York side, they really had to go down twice that far before they could hit bedrock. So the caisson, they wanted to, it's going to carry a lot more stone before it came out of the water. They built it, they had another 10 feet of wood to the top of the New York side, so that was 31 feet high of wood. If it was solid wood all the way up, there'd be about 4 million board feet of wood, timbers, in this caisson. It was at least 20,000, 12 by 12 by 18 foot long timbers pulled together. Yes.
You said yellow pine?
Yellow pine.
How come they picked yellow pine?
They used yellow pine because it was full of sap, and it's actually dense enough that it wouldn't float. And it's very long lasting yellow pine. Though they did use white oak on the very few bottom courses right in here for the strength of it to deal with the loads of the weight pushing down. As it lowered this up, it just sort of pushed its way. They just let it settle, is what happened here. Now the big problem on the Brooklyn side was the digging was in sort of a glacier till, and there was a lot of stones in it. And they had to get the boulders out from that cutting edge, because the boulders would start denting it. So they make sure they had to stay ahead of the boulders as the thing settled. Plus, where these chutes went down, this is all full of water in here. They had, and right here is a pool of water. It's kind of like a barometer or a thermos type of arrangement. They had to make sure that these chutes, no stones are underneath them as this thing, so they had to keep that dug out in there. So this is something that's all brand new. They didn't know if this was going to work or not. It's really quite surprising, you know, to think about tackling this and seeing what's going to happen.
And what about the oxygen down here?
Now what happened, to keep the water out, they had to fill it up with compressors. They had compressors working. They had on the Brooklyn side, they had 6 compressors run by steam. Each compressor had its own steam engine. Each compressor was, for people who understand like engines, was 4,000 cubic inches. That's how much the displacement of the pistons that were working to push the air in and keep the pressure going. The air was leaking out all the time. And in fact, on the New York side, the pressure was going to get high enough that it would actually push through the wood itself. going down 90 feet. Let's see what else about them. The key was that, you know, first getting it settled, as they got the wood on, then they started putting stones on it, and it finally would rest on the bottom of the river, and it wouldn't move on. Now, they did level the river a little bit before they brought the caisson in. They kind of dredged it off and cleaned it off so it was relatively level as they could make it, and then they started its downward descent. The New York side, the digging was way easier than on the Brooklyn side. They actually got to a point where it was just a layer of sand. In fact, when they first started, they first dropped the New York one down. They only did it was in an area that was part of the dump area for the city, and the sewer line was still coming in there, so it was all mucky. You know, what we think of sewer, and dead animals and things like that. But they eventually got down to where there was just pure sand that they were digging. And here's where we get into where Tom was talking about the dirt flying out through the top. On the New York side, they were done with the Brooklyn side when they started the New York caisson. So they used some of the things they learned from the Brooklyn side to work in New York with. They knew they had to go twice as deep, so they increased the compressor strength. They had 13 compressors working on the New York side. And they put 50 holes up through the wood of 4-inch pipe. And they let the air just sort of go out through that pipe. They could open up the pipes and close them. And they could take that sand, and they started out by just taking the sand and putting it next to the pipe where it was going through the roof. And then they'd open up the pipe, and the air pressure, just like a sandblaster, would grab that sand and go right up through the pipe and out. They didn't have to use the clamshells to do the digging with it. And then they got down deep enough where they didn't have to close it off anymore. They could hardly keep up with keeping enough sand in there to go up through. Now that sand, remember I mentioned sandblaster? That dirt would come out through the top of the pipe up here. It would go 400 feet in the air. And so they put an elbow on it to sort of direct where the sand was going. Well, in 1 hour's time, it blew a hole right where the elbow was. And then they made a special cast iron one that they ate up in a day. And then they started putting granite blocks over these pipes to deflect the sand that was coming up. And in 2 days, it would blow a hole right up through it, sandblasting. But it did save them the exercise of trying to deal with using the clamshell to carry all the dirt up and out on each one. They mentioned fire. Go to the next slide and see what we're at. They didn't say anything about the fire. The fire was a huge, huge issue. And Roebling realized that when you're dealing with compressed air, surrounded by wood, that it's just like when you take a coal and you blow on it, it'll start growing. Well, they had lanterns and stuff down and below, so they were worried about fire. Apparently, on one of the petitions, next slide, right in here somewhere, a guy left his lantern up near the ceiling, and the flame got up in between one of the cracks. It started burning, and they didn't even know about it. And then finally they realized that it was burning, and they tried to extinguish it by blowing steam up into the water up in there. And they thought they extinguished it, and they kept working, and then this was on the Brooklyn side. They were 2 feet from bedrock. They only had to go 2 feet more before they filled the whole thing up, and that's what they did once they, sort of a side note, once they got down to bedrock, everybody would get out, and they would fill this whole bottom cavity was filled up with concrete. So it's not anything that's worth concrete. It was a little more complicated than that to try to fill that up with concrete. But ultimately, when everything was done, it was bedrock, concrete, wood, and then the stone going up through. Rowling didn't want to flood the chamber. He knew he could flood the chamber to put out the fire. Now, they didn't know where it was up in the wood. They just knew they had, it was going up there. They drilled up into it to see where it was. Every time they drilled into it, then that allowed more air to go up into it and fan it. And finally, they realized that they had to flood the chamber to kill the fire. So everybody was out, and they had all the fire departments around. They were 45 feet down at this point, so no water was coming in from the sides of it. And they had all the tugboats squirting water. They would squirt that water in through the top here, and the water would come in and float it up. And he was worried about the fact they had all that air pressure in there. That air pressure is help holding this wood up, just like the dome, the Teflon is held up at the dome. That air pressure in here is helping hold up all this wood with all that weight of the stone on it. And he wanted to make sure that the air was coming out at the same rate that the water was going in to keep everything in equilibrium. It took 6 hours for him to fill it up. It was over 1,300,000 gallons of water, whatever. It took quite a while to fill it up, and they just let it set for 2 days to extinguish the fire. And then they went down and in and started doing the finish work, finishing off the thing, and they decided they wanted to do a test boring to see how bad the fire was in there. They thought they could just sort of push concrete up into the areas, and they forget the exact reason why they didn't do it. They realized that they had to actually cut out a chunk of the roof and go up into where it was. And when they cut that out, and they got up in there, they saw that timbers, huge areas of timbers had burned out. And it was just charcoal in there. And it went down, like veins of it would go down the timber. It would burn. It wouldn't burn on the two sides, it just burned that one timber. And so for 3 months, they had 30 men down there working, digging out all the charred wood and going in there just on their backs, going through in between those layers of wood, taking all that out and sliding in a new piece of wood and filling in between with concrete. Because they had to have, it had to be solid timber there, compression-wise, to pick up the load. So it was a huge deal, this fire. On the New York side, what they did when they built the caisson is they covered the outside and the inside with metal, so that there was no wood exposed to it. Also, when they built the caisson, they did fill it up with all kinds of caulk and tar and things like that to keep try to keep things as tight as they could with it. Any other thing? I should mention too about the bends situation. This is when they first started getting involved with the problems of your body being under compressed air and then decompressing real fast. And on the Brooklyn side, they went down 45 feet. They did have some people that were getting the bends, but nothing was really serious. On the New York side, they were going down, digging real well. They were down 60 feet or 70 feet, and then people were starting to get sick quite a bit, getting sick from the bends. And they had a doctor there that was trying to figure this out. And they actually did sort of figure out that it had something to do with the decompressing. And they did sort of expand the time it took, to decompress themselves. They didn't realize, though, it took hours on the decompressing, so that the nitrogen in your system would stay, instead of bubbling up, would stay in solution in your bloodstream. But they got down to 70 feet, and the digging got into an area what they call quicksand in the book. But it was sand that they could hardly pick through. It was like concrete. And he was still 20 feet away from bedrock. And he was also 20 feet away from the first bedrock. And they did some other test bores, and the bedrock wasn't level on the New York side. And they had to dig down through the early bedrock to get a flat level. And so at this point, 2 men had died from the bends, And Roebling had to make a decision on what to do. He knew that if he went down to bedrock and had it level all the way around, it would take about a year's worth of digging at this point. He figured he'd lose about 100 men from the bends. And so he decided at this point, it was his decision alone, to stop the caisson on the New York side at, I think it was 76 feet, 78 feet. 78 feet 6 inches from the high water mark. And the top of the towers were only 3/4 of an inch out of plumb, out of level at that point when he did that. And then he filled that, pulled everybody out, and they filled that all up with concrete. So the New York Tower is not setting on bedrock. It was setting on, and I say sand, but it was sand, it was like concrete at the time. It was very difficult to deal with, but it's not on bedrock. Next slide.
So how many workers perished? in the
Just
entire
two.
site?
Just two on the digging is all I know about. I don't know if anybody else died from any. There was about a half a dozen. There was a couple, one strand busted, and there was another thing that let loose. There was one guy that fell from the upper tower down through the holes in the tower, and he landed on a bunch of barrels, and he lived. They couldn't believe it. They were thinking they were going to go down and pick him up, and he lived. This is the New York side of the building, of the tower, and that tower, like I said, is just resting on sand, 78 feet below the high tide mark down there. Now this bridge, I did forget to show, it dominated the skyline back in the, I'll give you a second. It dominated the skyline in the 1880s. It was, the only thing that came close was some of the churches that had a spire that went up that high. But this was a tower that was 100 feet by 160 feet, almost 300 feet in the air. In fact, there was nothing like it in the world. It was what they considered the eighth wonder of the world at that time. But today, you look at the Brooklyn Bridge, and it's just a slow little thing down on the New York skyline. Next slide.
Did you have a question?
Yeah. Have the 150 years made any difference on it sinking down into the sand? Or?
I don't know. Like I've only one red book, sort of like some of the. There's an awful lot I don't know. I'm just sort of throwing out some facts that I run across. Has it settled at all? There's a lot of good questions, that's for sure. Yes?
Regarding the caissons, they didn't have to do caissons like in Pittsburgh and stuff? I mean, he had no
If you notice the picture of like the bridge in Cincinnati, the bridge, it was on, the water was way low and they were on dry land and they dug that out.
For the towers, yeah.
They didn't do them there. The caissons, this is a new thing that was just sort of started, to wrestle.
When do you think the caissons are still there?
Those two towers,
Yeah.
right there, are setting on wood. And it's setting on wood for almost 140 years.
Yeah, but the wood is filled in with concrete.
No, there's a layer of concrete. There's the concrete in the air chamber, but then there's the wood, and then on top of the wood is where the stone takes off. So that wood is still there. Now, the reason it hasn't rotted out is because once you drop down below into the surface far enough where there's no oxygen, the wood doesn't disintegrate. It gets eaten up by organisms. And where there's no oxygen, there's no organisms down there to eat it. And so that's why when I did this presentation for my timber framing buddies, there was a lady there who does archaeology on Lower Manhattan, and she talks about when they get down, there's a special name for the zone, I forget what they call it, oxygen depleted zone. They come across organic matter that's fine. It's no different than it was 200 years ago because it's not being heated up. So that's why that wood, does work. So the Brooklyn Bridge is being held up by timbers, not steel or stone. Yes.
I read the book quite a while ago. At some point, didn't Roland get sick or something, and he lived in an apartment
Yes.
and just watched from his windows?
Yeah, John Roebling died because of the getting tetanus, lockjaw from the boat, and then Washington Roebling, he was down in there doing this, getting into the compression, decompression. From 1870, from the mid-70s, I think it was 1876, he never went back to the site. He wasn't for the next 9 years, or 7 years, he was never back to the site. He watched the progress from an apartment along the East River, looking at it, and his wife was sort of the communique with the engineers. And that one picture that I showed of all those men in the hats next to the acreage, those are, a number of those people were engineers. And they, the average age of the engineers was only 31 years old when they started. Of course, it took 14 years to build the bridge, so they're a little bit older than. But no, he never really recovered from the bends. He always had, and they, only a year from the completion of the bridge, there was a group of people that wanted to get him out of the engineering of it. But his mind was still okay. He could deal with the engineering. He just wasn't on the site. And the other engineers, they had their time to make it work. Any other questions?
Any more slides?
There's more slides, but.
Can I ask a question? This one, Randy. It's probably a very simple answer, but a suspension bridge, the concept, you see where the center is, what is the force, the downward force in the center? Is it simply the weight of the platform that's going across?
Well, the curve itself, there is this optimum, and it's just the natural resting of it right there. It just naturally wants to rest there. They start pulling it, and it starts getting tauter. The higher up you pull that curve, the more tension on the cable. And so they have to come to this, and there's a part of it has to do with aesthetics. This is where John Roebling wanted it to be. And if you've seen pictures of the Brooklyn Bridge, particularly at night, it has this beautiful arches to it coming across. And that, I'm sure there's engineering involved in it, and I don't know what it is. But really the key is that people think of bridges, the key to bridges is not all the traffic that's on it, it's the weight of the bridge itself. If you can suspend the weight, that's what's important. And in this bridge, like I said, that the actual total weight of all the cables and this structure was 20 million pounds, and each one of these cables with those 6,000 little wires in it could carry 24 million pounds. So they had 3 extra cables in there carrying all that weight.
Randy, what was the cable diameter?
The actual diameter was 15 inches, 15 3/4 inches, about 16 inches. Not big. This is, that's 16 inches right there, between my 2 fingers. Not very big. Steel has tremendous tensile strength. 40,000 pounds per square inch worth of tensile strength. Compared to a piece of wood, a piece of pine is like 800 pounds per square inch of tensile strength before it pull apart. So steel is quite, and then steel was the first that was used in here. Now, sort of a side note, I shouldn't tell you, you won't go on the bridge. There was a to-do about where the steel was supposed to come from to do the bridge. And Roeblings made steel rope, but they were the designer of the bridge. And so there was some other people said that we should have an opportunity to bid on this. And so this other company, the Hague Company in Brooklyn, got the job to furnish the wire. But the wire, Washington said, I want to be able to test that wire though, because I don't trust these guys. I want to be able to test each spool to make sure that it had the strength it was supposed to have. So they made the wire in Brooklyn. They would send a spool up to this testing spot. They would test it, and then it would go onto the bridge. Well, what happened early on was that what they did is the manufacturer went up with a spool that tested okay. They took that spool back to the plant. They kept running that spool up and back and sending spools that didn't pass, they sent them on.
Oh,
And actually, what happened, one of the engineers noticed the wire was very brittle, and he took it to Washington, and he looked at it, and it just snapped. He goes, "What the heck is this all about?" So come to find out, they realized they were putting in wire that was inferior. So they added 150 wires, I guess, to each cable to try to deal with sort of the inferior wire. At that point, the wire was in the cable. You couldn't take it out. You didn't know which one it was. So they had to make a decision on what to do with that. So that guy ended up in jail because of that. Yes.
The premise that Brooklyn and Manhattan were separated by water, so a bridge was, they felt was a necessity. What's the reason for building the bridge?
Well, yeah, there was ferries going across all day long, back and forth. And it was, they felt that they wanted to, they did mention that the river froze south back in the late 50s. And for a while, people were just going back and forth, walking back and forth, and wagons going back and forth. They said, geez, this is wonderful. We really need a bridge. So we can do this all the time and not worry about the rest of the ferries. So once it was done, there was people that, 14 years, over costs, there was always people that were saying we're wasting our time and our money. But once it was done, it was considered a wonder, and it was it's certainly 100 and whatever 40 years later, it's a landmark of the world. And even with those rotten wire in there, it's still standing. Yes.
It's the highest height from, like, say, in the middle there down to the top of the water.
From the sea level up to the top here is a little under 300 feet.
Okay, now you go to the middle of that, between the two, yeah, right there down to the water, how high
That
is
was
that?
130 feet, 135 feet.
So ships do go under it.
Pardon?
Ships still go under it, not ahead of time.
Yeah, they had there was some criteria, and one of the criteria was at midstream that had to be this high so ships could go under it. Probably today there's ships that can, of course, they fold out, I don't know. When you look at the bridge today, like I came over on the Valenzano Bridge or whatever from Richmond over to Brooklyn, and I'm looking at the Brooklyn Bridge and I'm thinking, that bridge is huge, compared to Brooklyn Bridge is little today. But back then, it was a wonder of the world.
What is the longest suspension bridge
I don't know which one.
Well, we cross over from New Brunswick to Prince Edward Island, Federation Bridge. And you get off in the middle, you can't see either.
Isn't that something?
But I don't know if that's a suspension bridge or.
Did it have cables going on the side of it?
Yes.
Yeah. So that's a suspension bridge.
So it just has many more of the pier. But theoretically, you could, with enough caissons, you could add on either end of this length.
Oh, true, you could have more towers.
More towers.
Yeah. And they actually have some bridges now where it's just one pier, tower in the middle, going to 2 anchorages on the side. And if that was to happen too.
I haven't read the book in a long time. What was the one thing you could not do on a bridge? They had trolleys on it, they had vehicles of all sorts, but I remember there was one thing you could not do on the bridge. Do you remember what that was?
Now, it's been a year since I read it.
Supposedly you could not march across the bridge because the vibrations
That makes sense.
would set it, to jingling, I guess.
That's interesting.
Unless you were on a step.
That's why if they marched across, they had to do the riot step, except nobody was in step.
Well, they had actually, when it first opened up, they had, it was loaded with people, and they had a panic, and these anchorages at the other end were complicated structures of people getting up in there, carriers getting up in there, trolley cables, and it was loaded with people in there, and somebody panicked, and a bunch of people got trampled and died. On that end. I just focus, mainly my focus is on, was the timber work down the bottom, and the fact that there's actually wood holding it all up is quite amazing.
Well, sometimes I'm on a bridge and the traffic is stalled and there are all these semi-trucks and longer and longer. And I wonder, has that engineer calculated how many semi-trucks? And there was one in Twin Cities that went down.
One near Seattle, too.
Was it?
No, it does happen. I think the thing to think about there is in the mid-50s, they redid everything. They changed it into the 3 lanes, and like I said, one cable was enough to carry the whole weight. So 3 other ones, the semis, didn't mean much to the weight. Guess we're set.
Well, thank you so much. I have a quick related story to that bridge.
You own it? You own it?
Go ahead.
Good.
2001, my son, my friend Dave Brown, and my son's friend went to New York to the Big East games in March 2001. Wasn't a game until Saturday night after we did our Thursday, Friday night thing. And one of the things I wanted to do was go to the Twin Towers and walk the Brooklyn Bridge. We went to Twin Towers, and that's another whole story. And then we walked the Brooklyn Bridge. And there's big, wide walking ramps on there. We walked over to the Brooklyn side and walked back. And I was pretty impressed. And, then I've seen a little bit of this on the History Channel. Probably Randy, you've seen that or seen that special on building of the Brooklyn Bridge. So after walking across it, and I'd forgotten about the diameter of the cables, but it was enormous to look at. It wasn't like a piece of cable we'd have around the farm. It was amazing. Just wanted to mention that.
Did you feel the bridge sway at all as you walked?
Here's your walk. You missed the beginning of the program.
We didn't feel the bridge sway that much. It was a calm day. And we heard all those things, and what you mentioned about marching too. We had heard that.
A lot of these pictures came out of that program that you just mentioned. Out of the program that I had in the caissons, part of it. It was a way to grab them quick.
I mean, it's been a long time since I drove across the Brooklyn Bridge. Is there a toll on that?
No,
Was there ever a toll?
I don't think there was. Who knows after 140 years? What would have popped up?
A lot of bikers too.
Yeah.
Chuck, I got a
Okay.
story to tell you. I drove school bus for Lafayette, and I had the Onondaga Indian Reservation School, and they were going down to the Bronx Zoo. And we were going across the bridge, and none of them have ever gone across. They go, "Hey, Lorraine, is we gonna fall in?" And I go, "I hope not." And, you know, and they want to know, is it moving? They could have swore it was moving. No, relax. Here I am scared to death. And I go, "We're getting across." So I get across, and I turned on a one-way street, and I was supposed to go on it with buses or trucks, but we got off from it. And I'll never forget that, but it was interesting to go on it. So I can grow.
Well, we got some refreshments here, folks. You can share some more stories, and you really learned something, didn't you, today?